Good morning, good afternoon, good evening, even good night, as it suits the current location of the sun in the sky in your part of the world. I am Akhilesh Latikia from the Pennsylvania State University, and my co-host is Professor Jamesina Simpson of the University of Utah. Welcome to the first electronic lecture of the U.S. National Committee of the International Union of Radioscience. We hope to have 4 lectures every academic year, taking advantage of internet resources that bring worldwide audiences together. Please note that this lecture is being recorded and will be made available through the internet. Today's lecture is on the use of artificial intelligence and bio-inspired computational techniques in applied electromagnetics. Although this research topic has been around for about 20 to 30 years, explosive growth worldwide in computational power and AI techniques in the last 5 years now is letting us handle truly complicated problems. Our lecturer today is leading from the forefront. He is Professor Magdy Iskander of the University of Hawaii in Manoa. Professor Iskander obtained his degrees from the University of Alexandria in Egypt and the University of Manitoba in Canada. He joined the University of Utah in 1977, where he became a full professor in 1985. He began a successful engineering clinic there the next year, followed by an NSF center dedicated to computer-aided electromagnetics education. He was a program director at NSF in the late 1990s. In 2002, he moved to Hawaii as the director of the Hawaii Advanced Wireless Technologies Institute. I was his first PhD student, so I can tell you a lot of stories about him, but I won't now, except to show you 2 festschrifts that have been written to commemorate the legend in applied electromagnetics that Professor Iskander is. Here is the first one, and here is the second one. Both books contain detailed accounts of his research accomplishments and numerous recognitions, and he continues to stride forth purposefully in the realm of applied electromagnetics research. So please join me in welcoming Professor Iskander. The next 50 minutes belong to him, followed by a Q&A session. Magdy, all yours.
Thank you very much for a very kind introduction. Hello, everyone. Thank you very much for joining us in this lecture series that is organized in order to stimulate interest and promote innovation in applied electromagnetic research. You already heard that my name is Magdy Iskander, and I am from University of Hawaii. I'm making this presentation on behalf of my colleagues here at Hawaii Advanced Wireless Technology Institute. And as you heard from Professor Akhtakia, the title is Artificial Intelligence and Bio-Inspired Computational Techniques in Applied Electromagnetics. The presentation basically has 3 components. The first one, basically a very brief overview of artificial intelligence and bio-inspired computational techniques. But the focus of presentation is on 2 applications. The first is related to the use of genetic programming to develop and design advanced metamaterials. And we will show that through genetic programming, we're able to design metamaterials with characteristics, very important, that far exceeded those who are possible using human expertise. The second part, or the second application, will be on the use of AI to calibrate and enhance the application of a medical device, that is the cardiopulmonary stethoscope device. We have patents on this device, and we'll be introducing the concept of virtual clinical trials in this presentation. At the end, we'll briefly describe 2 additional applications, one in the propagation modeling area and the second one is a smart power grid with its a renewable energy kind of application. Well, let's get started. The bio-inspired designs are basically designed and inspired by biological evolution and the use of the process of natural selection in order to converge to an optimized solution. The use of these techniques have grown significantly lately because of their track records. These techniques have delivered designs that far exceed those where possible or can be achieved based on regular and traditional human expertise. We will be discussing some application in the area of metamaterials. And in the metamaterials, as you can see here, we will be talking about materials that have characteristics beyond what you can find in nature, like perfect magnetic conductor, or an absorber that have absorption characteristic beyond what you can achieve based on materials available in nature. We will be using genetic programming in these designs, but there are wide variety of these bio-inspired computation techniques, neural network, genetic algorithm, swarm intelligence, and genetic programming. But we'll be using genetic programming as our main design tool, and we use genetic algorithm as a low-level optimizer of these devices, just in order to improve the computation efficiency. They look different, and they look different kind of approaches, but they all have really same fundamentals. They are all population-based, trial and error techniques with some optimization algorithm somewhere there, and that optimization algorithm is often based on biological evolution and the natural selection point of view. So they all have the same kind of foundation. And the conversion towards the optimized design is guided by what we call a fitness function, which is basically a figure of merit that tells us how a specific design at a specific stage of this trial and error does approach the design objective or a set aims from that design. Here we go. I talk about genetic programming and the genetic algorithm, but I need to emphasize a couple of points here. From the machine learning domain or from the global framework, which is represented by the blue background here, ocean kind of thing, these techniques look different, like different separate islands. But if you look beneath the surface, which is a slide at the bottom part of the slide, you see that these techniques have joined really foundations. And that is particularly true for genetic programming and genetic algorithm, because they share the same foundation of biological evolution and the natural selection process. But we need to keep in mind that genetic programming, which is the right side of the slide, and the genetic algorithm are really have significant differences. So genetic algorithm, the top part of the right hand there, you can see that the number of genes between different generations of the solutions are the same. And all what genetic algorithm does, it improves in the characteristics of each gene toward achieving the design objective. So what you are seeing here is that we maintain the same design in the genetic algorithm and just improve on the characteristics as a function of these different iterations. Genetic programming, on the other hand, which is the bottom part of the right hand there, new generations of these designs have different number of genes, which means genetic programming, you create new topologies, new designs. And therefore, from this point of view, genetic programming, of course, had provide more capability to achieve the design objective than genetic algorithm. And that's why when you look at the bottom part of the of the left-hand side of the slide, you see that genetic algorithm is a design, while genetic programming is a designer, because it evolved into different design geometries and topologies as a solution continues on. So how do we use this genetic programming and genetic algorithm to design metamaterial? You do have here this flow chart, which shows that we start with a collections of programs. They're all programs, collection of programs to address different design aspects of the metamaterials. And then out of this, out of generative population, I'm going to show you how we do that. We will be able to put together a design that can be modeled and simulated on high frequency structure simulation. We send that simulation, we calculate the S parameters and see if we are achieving the design goals. And before we send it back to assess it based on the fitness function, we may go through some genetic algorithm to enhance the design performance that is generated in this area version of the design. Then we send it to the fitness function and compare it. And as long as it's not satisfying the desired characteristics and the desired aims, we redesign or we formulate another design. And the way we formulate the new design using the biological evolution, namely your reproduction, take some from the older design to the new design, crossover from multiple parents, we calculate new designs, and sometimes we introduce some mutation which are arbitrariness in order to enhance the conversion process. So what we're seeing here is the genetic programming in creating a new design is basically a bunch of program addresses different aspects of the design, and each program has certain functions and center operation and certain constants. And we put all these pieces together and try to come up with design that continues to evolve as a function of multiple iteration and using the biological evolution and natural selection process. And we continue to evaluate it again as the fitness function in order to achieve the design goals. So to go in detail, more details, we start with the pattern generation. And the pattern generation, for example, that's one component of the metamaterial design, is created by these polygons of conducting material or the resistive sheets or whatever material we use in metamaterial development. And we created hundreds of these. This is what we call the populations. And the way we create this 100 by the number of vertices, the location of vertices, the distance between the vertices. So we created hundreds of these. And then we combined some of them in an initial design to create a pattern, as you can see in the bottom there, create a pattern, and that will be the patterning part of the program. Then we move into another program, part of the program, and that has to do with the substrate optimization. Here is the number of layers of the substrate, the properties of the substrates, and the thickness, and so on and so on. So that's another part of the program. Then we combine all this in a specific metamaterial design that can be evaluated by HFSS. So it's a simple process. And at the end, what we have here, that's represented better. Here is an example flow chart of a program. So you have these global parameters, which mean the frequency band and the desired characteristic and fitness function and so on. That is on the left-hand side there. But you have different parts of the program, as you can see here. One of them is for the substrate optimization. And if you look at the bottom of the substrate section, you are changing the loss tangent, you're changing the dielectric, the thickness, and that kind of stuff. And then there is a patterning part of the program where you are creating new patterning by including more of this building block, or what we call the population elements, or changing the distance and rotation between the population elements in order to continue to enhance the design. But I also want to point out that under the patterning part of the program, there are additional branching that you can also include in order to continue expand the capability of the genetic programming in order to produce and achieve the features or the characteristics of the metamaterial that you're trying to design. I think at this point now, we're going to give some examples of developed metamaterial design using genetic programming. One of those is, once again, we're going to use perfect magnetic conductor. That problem was particularly challenging because the required frequency range is low frequency, 225 to 400. That's required by the sponsor in order to pack one of their array antennas. And we were able to achieve that using 3D metamaterial design. And this design is particularly attractive because it's all made of material that's available in our labs or any labs. We don't have any conducting sheets, we don't, what you call this, magnetic sheets. We don't have resistive sheets, and we don't have any of these gimmicks. But instead, what we have is a 3D design of this metamaterial structure that satisfies the requirement of broad frequency band in the in the very challenging low frequency range of 200 to 400 megahertz. Unfortunately, we weren't able to fabricate this because we don't have 3D printers that do plastics, dielectric material, as well as conductors. We only have 3D printers that do dielectric materials. So if anybody who is listening has one of those fancy 3D printers that do metal and dielectric at the same time, and if they are willing to cooperate, by all means, we'd love to send them HFSS files, and we can fabricate this and experimentally verify it. What we can actually fabricate and experimentally verify is metasurfaces, a two-dimensional design. And in order to emphasize the significant advantage of using genetic programming, here we have some design that published in literature, and we're trying to get the same characteristics, and we'll try to get it designed using genetic programming. So in this example, the figure here on the right-hand side is the one in the literature. Traditional metamaterial design, rings on dipoles, resonances, and so on. That's very good. And then you have multiple resonance there, so it provides broadband characteristics. But look at the left-hand side. That doesn't look like anything that could be used based on human expertise. Yet, when you look at the curves, the magnitude and phase of the S parameter, you see that the metamaterial designs outperform broader band compared to the design that was achieved using human expertise. Another example of that is the one here. Once again, here is a design, traditional human expertise kind of design. Look at the metamaterial, the genetic programming design. Doesn't look like anything that designed using traditional electromagnetic ideas. Yet, you see the one created by genetic programming, once again, outperformed the one that was based on human expertise. I also want to point out that if you run the genetic program using the same fitness function and same characteristic twice, you may end up with two different designs because it's all based on trial and error using this population that you created at the very beginning for patterning and so on. So in this design, you can see the one on the right, that's human expertise, and the two on the left are two designs that came up out of the result of the genetic programming. And in both cases, the genetic programming, of course, outperformed the one based on the human expertise. Now, these are two-dimensional structure that we generated using genetic programming. Therefore, we can actually evaluate this result experimentally. And then you can see the result, experimental result, we're in reasonable agreement, good agreement with the simulation values. But I also want to take this opportunity to share with you the fact that we're lucky. We actually built here an indoor antenna range, and we have a network analysis lab with seven network analyzers. And we also have wireless test bed. So if you are interested in pursuing your graduate degree or postdoctoral fellowship or even sabbatical, we have the experimental facilities, we have the simulation capabilities that can make your stay here at University of Utah or your graduate program. Sorry, University of Hawaii. The University of Utah is my previous university. They are still friends there. Yeah, you can make your stay at University of Hawaii very productive and attractive as well. We also compared design of absorbing material. All this earlier example was were perfect magnetic conductors. So now we're talking about absorbing metamaterial. And here we're comparing the left-hand side is the genetic programming one. And the one on the right-hand side is another computer-based design, is using pixelation approach, different pixel in different locations and so on, in order to achieve optimized design. The one on the left, the genetic programming, doesn't look like anything that can come up out of regular human expertise. It's a very strange looking shape there. And I'm emphasizing this point because later on I'm going to discuss it. But as you can see from the results on the right-hand side, that the genetic programming design outperformed the other computer method design, the pixelation method, at all level of biasing of the graphene. That was all graphene-based designs for 4 volt per nanometer and 2 and 0.5 in all cases. Genetic programming design outperformed the pixelization computer-generated model. So while talking about graphene and so on, I also want to share with you that recently we had a research project in which it was needed that we design absorbing material. So we're going to talk about graphene absorbing material, but in a compact radar frequency range, which is 1 to 11 gigahertz, is a low frequency. Therefore, talking about laser-induced graphene and the abilities to make this large size board in order to validate experimentally is extremely difficult. We also considered, so the laser-induced graphene was difficult to even think about, although we considered it. We thought about carbon fibers, and we ran into this isotropy and non-isotropy issues. And if you put it multi-layers, you don't know what is the properties of these layers and so on. So we run into some design issues of how to deal with this broadband absorbing material in the low frequency, in the compact frequency range, radar frequency range. But we ran into these conductive films, rolls that available at the company. You have the website for the company at the bottom of the slide, coupling. And they were even reluctant to send us their material because they didn't know that would be of any value to us. But anyway, we insisted. We got the material, we got the properties. It's about 200 ohm per square. And we designed some metamaterial using these properties, and it was successful and sufficiently broadband in the compact radar band. But how are you going to fabricate this? And here comes the big break for the project, namely the use of vinyl cutter. Very simple, my God, very simple fabrication process. And you can see at the bottom of this where the sheets are coming out. I'm trying to point it out here. Where the sheets are coming out of the roller there. They are all cut, and we remove the extra pieces. And all of a sudden we have our metamaterial sheets that we're able to evaluate experimentally, as you can see here in our anechoic chamber. And as you can see, experimental results agreed reasonably with the simulation results, even for different incident angles. And we found that actually this design will maintain its reasonable characteristics, even if the incident angle is 45 degrees. Actually, even if the 60 incident angle is 60 degrees from normal, but with some deterioration in the performance. So it's a very nice broadband design that we're able to deliver to the sponsor. Well, so far, so that's what we have been able to do. 3D metamaterials. We have here lenses, multi-layer metamaterial lenses that we develop for antennas. And here we have meta surfaces, and we have absorbers, we have 3Ds. So it has, genetic programming has been very good thing to use and achieve many of the design objectives that our sponsors were asking of us. The problem is when people look at these designs and they look at the advanced characteristics, yes, you can experimentally verify, but can you really explain if this thing really follow the electromagnetic concepts? How all this strange looking geometry or topologies of metamaterial actually, why it works the way it works, and does it really comply with the fundamentals of electromagnetics? And to help us answer this question, we pursued two approaches. One of them is the equivalent circuit approach, as you can see on the left-hand side of the slide, whereby we calculated the inductances and capacitances and fringing capacitances and all kind of little things, detailed topologies and detailed structure involved in the metamaterial designs. And out of this, we developed equivalent circuits, and we ended up having, a considerable number of resonant frequencies that are overlapping, and that's why you end up with a broadband design. We further confirmed this approach by doing Bruni methods on the right hand of the slide here. And in the Bruni method, as some of you know, we have a 10 lambda by 10 lambda board, 10 by 10 lambda board, and we irradiated with RF pulse, broadband time domain pulse, RF pulse. And after you look at the scattering, and after removing all the scatter feed and so on, and you only look at the late time signal, the small signal, the late time signal. This is related to the natural frequencies of the structure. And if you go back to the frequency domain, from time domain to frequency domain, you will be able to identify the natural frequencies of this irradiated geometry or device or board. And surprise, surprise, of course, we found that the natural frequency agrees with the frequencies that were created from the equivalent circuit model. It's a very nice piece of work. I particularly like this. Of course, it is published somewhere. If you want copies, we'll be happy to send you to. So now we have to summarize that we use genetic programming for metamaterial designs. Yes, these designs achieved characteristics that far exceeded those who are possible using human expertise. Yes, we verified this experimentally because we have nice labs. And of course, we're able even to explain that this design do follow the fundamentals of electromagnetics. What we're doing now is trying to go to active metamaterial design. So it's active, reconfigurable metamaterial design. And we have, of course, some of our graduate students working on that. So now that will help us move to the other topic. Another topic has to do with the use of artificial intelligence in order to calibrate and extend the capability of one of our medical devices. Just a brief word on the background of artificial intelligence. Of course, they're affecting all aspects of life. We know that. And they're involved in a wide variety of applications. And here we're going to talk an application in the healthcare area. But also, I want to mention that it is of interest to us, application in education. That's one of my very close to heart topic. So if those of you who are listening, if you are interested in artificial intelligence in education, the use of ChatGPT in education, in guiding simulation, in guiding virtual lab experiments, and so on, please consider submitting your papers to Computer Application in Engineering Education by Wiley. That is a journal that I started in 1992, and I have been its editor-in-chief since then for a total of 32 years. So if you are interested in AI, ChatGPT, in engineering education, very important, we're very focused. Please consider sending your papers to the Computer Application Engineering Education Journal. Now, we go and talk about artificial intelligence. And as many of you probably know, there are some supervised way, that regressions and classification, and unsupervised like clustering. And there are others that we call reinforcement learning. And this is really about exploration, about state, and then actions and reward. So they are different. What we're going to do here is to use clustering and classification in calibrating our medical device. And then we're going to use the reinforcement learning approach in the smart grid kind of renewable energy project that I'm going to talk about in the end of this discussion. So there was a reason why I'm showing you this, because we are using two of them for the medical device, another one for the renewable energy project that I'm going to talk about later. So what kind of device, medical device, you're trying to calibrate and extend its capability? Well, that happened to be the cardiopulmonary stethoscope device, which is a chest patch device. So chest patch device, we measure the S parameters, and out of the S parameters, we will be able to calculate vital signs as well as changes in lung water content. We've been working on this for a while. We have several patents on this device. And the device, when you measure the S parameter, the results are sent by Bluetooth to a tablet. And what you see in the tablet is a signal like the one you can see here on the right. And basically, the low frequency oscillation there is the breathing. The high frequency niches here is the heartbeat. And the change in the baseline is the change in lung water content. Well, we've been, as I said, working on this device for a while. But let me mention one more thing. Changes in lung water content is a cornerstone to managing many important diseases, heart failure, kidney failure. We even published paper about the using our device, a cardiopulmonary stethoscope, for monitoring COVID-19 patients. That we published that about a year ago or something. So measurement of lung water, and our device measure vital signs and lung water content from a single microwave measurement. Another picture of the device you see here is a small device. The sensors are patented because you have two microwave sensors there, one for transmission, one for receiving, and they are characterized by strong coupling to the human body with minimum external leakage, because if there is any leakage between them, it of course will dominate the signal. And the device is safe, as you can see, is safer than any of the cell phone. We calibrate against the cell phone, and the SAR, the specific absorption rate, is lower the safety limit that was set by FCC. So it's a safe device, it's a small device, it's a low cost that can be used for continuous monitoring. And I even have a video clip for you here. You can see, you will put the patches on the person, and then you see the signal that I just showed you. We tested, we had very lucky to have an NIH funded clinical trial. That's very important. And that has two parts, part on trying on healthy people to compare the vital signs, the heart rate and the breathing rate. And we compare those with FDA approved devices, and the correlation factor here, as you can see, is excellent. What we have here is healthy people on a treadmill, and large number of medical people actually was watching this to see if the device really will deliver what's supposed to deliver. And certainly people are very impressed. And even we have changes, measured changes in lung water. And here we tried it on heart failure patient, where our measurement were compared with the wedge pressure measurement, which is the pressure, blood pressure measured when you insert the catheter inside the heart. That's supposed to be the golden standard of monitoring lung water, inserting a catheter in the heart versus our chest patch device. And you can see the correlations are very acceptable here. And we also tried it on dialysis patients where we compared the microwave measurement against the loss of weight during the dialysis process. And as you can see, very impressive correlation factors in the 0.9 or 90% agreement. So far, we have very good results from the clinical trial. NIH, I keep saying NIH because it's very important, very hard to come by, approved clinical trials. And although medical community tell us having or measuring the change in lung water is really all what they need because they can use it in order to monitor reaction to medication or recovery from surgery and so on. So that's really all what they need. People still insist it will be really nice if we can use this non-invasive simple device in order to provide some quantitative assessment of the water in the lung. Namely, can you tell us if it is a normal lung or lung with edema or something in between? So that will require another huge clinical trial and comparing with very aggressive and invasive techniques. But here comes AI to the rescue. Our team identified, Dr. Yun and his team identified, why don't we use the large database available in NIH website? So we have huge CAT scans and X-rays, images available in NIH website. So we can digitize those, put our sensor on them, change the lung water content. So as you can see, the chart here is very descriptive. You start with the CAT scans on the bottom there, and you digitize it, and you do HFS simulation, and you change the lung water, and you build the database. And then on the right-hand side there, you combine this database with the data like age and sex and size and so on of the patient, together with the artificial intelligence algorithm, and we'll be able to come up with an assessment of lung water content. Big breakthrough for our project. And here is an image of what we get from NIH-based database. And the one is a sample of details of how we extract the different. It's all using MATLAB kind of codes before we transfer it to HFS simulation. So if you look at the simulation procedure here, we have this CAT scans and X-rays. We digitize it, MATLAB code. We put the device in the right place where we usually use it for measurement. So there is some selection over what specific cross-section we use. And we use the frequency, the right frequency, and we keep changing the lung water content, the different values, and build the database that we can use for AI evaluation. Before I show you results of this effort, I want to let you know that Dr. Zhao is again on our team. He's an AI expert here. He wasn't sure which one of the AI methods he should be used. He wants, of course, accuracy, but he also wants simplicity of interpretation. So we tried many of them. The support vector machine, the decision trees, the neural network, random forest. He tried all of them. And what you are looking at here is the vertical axis is the phase, and the horizontal axis is the magnitude of the S21 of the S parameter. And what we're looking at, accuracy in classification, but also simplicity of interpretation of the results by medical community. And the winner here turned out to be the decision tree for its simplicity. So that's one thing that came out of this study. We used a database of about 200 patients, half of them male and half of them female, 125 and 125. And the other thing that we're trying to examine is we need really, instead of having all this population as one group, we can actually try to classify them as subgroups. And in this way, we can develop a decision tree classification for each group and to be more accurate and easier to interpret. But how can we cluster these groups? In what basis? So we know the magnitude and phase will be used for classification. So we need now clustering in time, or grouping or subgrouping type of criteria. And here we found the age is important. The thickness of the fat layer is important because it interferes with this parameter significantly, is important. Of course, the sex is important. And we spend a lot of time actually thinking about the importance of the size between, skinny, petite, normal, obese, and the effect of this. And based on the AI evaluation and permutation importance study, it turned out to be the size is not important. How come? Because our device is a chest patch. It's different if we're using from one side to another or from front to back. Here is the chest patch, and turned out based on that, the size is not of significant importance. That conclusion came out of the result of the permutation importance study part of the calculations. So based on that, of course, we decided to break this cluster according to age and the thickness of of course, male and female, and the age and the size of the thickness of the fat layer. And we use the magnitude and phase, of course, for classification. And of course, that turned out to be the diameter of the side of the person is not of an important issue. And based on all that, we'll be able to come up with these results. For female, for example, that's just one example of the result. For less than 50 age old, and the bottom one for over 50, and the one on the left for thickness of the fat layer is more, and the thickness of the fat layer thickness. And what you are looking at is the vertical is phase, and the horizontal is magnitude. And then the one on the left-hand side, which is easy to interpret at this stage, if the phase is within that range, regardless of the magnitude, that's normal. And then if the phase changes in this range, it becomes a moderate edema, and in the bottom part, it becomes a severe edema if the phase goes in that direction. The one on the right-hand side is a little bit more complicated because of the effect of the thickness of the fat, as I'm saying, that turned out to be an important parameter. And you really have to have a considerable reduction in the magnitude, which is on the right hand of the figure there, before you start having normal or assessment of normal lung water rather than lung water with edema. You do the same thing for the male. So in general, again, the male was easier to interpret the results here, and the effect of the fact thickness of the fat layer wasn't as much importance, based, of course, on 250 patients that we will be able to digitize and simulate in this study. So what I'm trying to show you here actually is very simple. You can see that it expanded the capability of our design using this virtual clinical trial that is cheap, that is safe, that is not time consuming, and based on huge database available in NIH. What is equally important that all these AI approaches that I showed you before, that we compared, they're all available out there. So what is holding us up from integrating these AI techniques in calibrating our devices, for enhancing the capability of our devices, for actually extended the capabilities of our devices, and that is, or our technology or our designs, and that is the message I'm trying to share with you here. At this point, I'm going to add application in a couple of more areas. And the first one is potential application of AI in propagation modeling. This is an area close to the heart of Dr. Yoon here, who spent years characterizing different propagation environment, including, of course, the land, air, and atmosphere. And the claim to fame here was in modeling urban environment and mountain environment in Utah and so on. So we modeled wide variety of propagation environment. And the most attractive was in modeling urban environment, because it was based on geospatial in the Google Earth. We get two-dimensional using the shades. We can build three-dimensional and use ray tracing in order to get propagation modeling analysis. So what we have here is wide variety of techniques that we use. We use finite difference timing, we use the ray tracing, we use parabolic equations, frequencies from high frequency HF in the 30 megahertz all the way to W band, dimensions and so on. And if you look at the bottom part of the left-hand side, you see that different terrains that we used in this simulation. Foliage we did, indoor, outdoor we did, metal frame windows we did, mountains, we did all kind of simulation capabilities and so on. That has been useful, of course, in establishing effective communication channels. But as the time has come to use this data to build the database, or these capabilities to build a database that can use for foresighted decisions. How can we adjust the communication parameters to maintain effective communication channels when you have a severe weather conditions or disaster mitigation situation? And that's what we are doing now, trying to integrate AI using this database. Again, we have the capability developed over the years. And now we're going to add to it AI, to use this database in order to have a foresighted decision. Specifically, while working with the Navy, in order to identify ducting channel, the most effective ducting channel under severe changes in the propagation environment, like weather conditions and so on. What ducting channel, what frequency you use, what height you use that you can adjust the height of your antenna for, and so on. So that's what we're doing now. And the other application that I would like to share with you is in the renewable energy area. Once again, we're trying to, in the renewable energy area, we're trying to develop a way to optimal control of distributed energy sources. It's not the power company anymore. Everybody has solar cell on top of his house, or many people have solar cell on top of his house. And how you control all this and have to have an optimized performance of the power grid. For this, actually, we're going to use the reinforcement learning. And the reason we're doing this, because this particular application, we don't have known model. We don't know what the model we should build in a typical artificial intelligence algorithm. Therefore, we use the reinforcement learning, which learn the preferred protocols or the optimum policies by interacting with the environment. So you have, as you can see in the bottom here, the agent here, the reinforcement learning agent, is watching actually the interaction with the environment, which include, of course, the solar output, the consumer demand, and the battery level. In our example here, we're talking about the battery level kind of application, how to control the battery level, release or charge, and so on. So we have the state, which has to be the solar output, as the consumer demand, and so on. And then you control the action in the bottom, you control the battery level, and there is a reward. So there is this exploration process that will help us develop this optimized protocol for adopting the optimum policies. So what specifically we did, we established an OI2 lab, and we connected also the lab to some smart homes to collect data and use this data on a predictive model, optimum control model, because there is a slow model, but there's an optimum control. And we had our reinforcement learning or a specific, in particular, imitation learning technique, observe these protocols or policies there, and try to adopt it in based on the collected database. And based on this, we have, you can see there, the data, the day, time of the day, the temperature, the weather condition, the wireless output, and so on, and try to include all of that in the predictive model and learn from the predictive model. Once we did that, now we learned the optimum policies, and we can apply it. And on a test database, you can see the reinforcement learning algorithm outperform, once again, the predictive model, which is presumably an optimum model, by a ratio of 2,000. Why this is important? Because now we have applied this in a broader sense, different energy resources, the wind and so on. We will be able to help the Hawaiian Electric and the state of Hawaii achieve its renewable energy objective, which goes 100% renewable by the year 2045. You have to do the same what we did in the battery thing in different wide varieties of environment, and all of this, and try to provide an optimum control of the power grid and achieve the renewable energy goal of the state. So what I talked about so far is some application of bio-inspired computational techniques with a specific application in metamaterial design. And once again, genetic programming developed designs had characteristics that exceeded those ones that are based on human designs. We were able to verify this result experimentally and also explain the performances based on fundamental of electromagnetics. In the medical application area, we already showed you how we expand the capability and calibrate a device and extend its usefulness for humanities. And using the low cost, using the virtual clinic trial concept. And at the end, of course, we talked about this additional potential application in propagation as well as in renewable energy. I hope you find this to be useful. But the message that I want to share with you, look, we're in a new era in electromagnetics. The era of using artificial intelligence and bio-inspired technique in electromagnetic design and application and so on. And as we watched here, it provides us with aspiration for innovation as well as expanded applications. So my message to you, what are you waiting for? Join in, you are welcome. Join the movement and let us take electromagnetic to higher levels of innovation, productivity, and service to the community. Thank you very much. I am done. Thank you for your participation. I really appreciated the opportunity to be part of this innovative approach of sponsoring these lectures. And I look forward to staying in touch. Thank you very much.
Thank you so much, Magdy. That was fantastic. I wish we were all in the same room so we could all applaud, but virtually we're all applauding. So if you had time, are there any, do you have a moment for questions? And maybe we can ask anyone in attendance, please don't be shy. Let us know what your questions are.
And I have my team here so they can jump in and answer questions if it is an area. Okay.
So feel free to unmute yourself or put something in the chat and you can ask your questions. While we're waiting, I had a question about it's not really electronics related, but the vinyl cutting, what do they typically use that for? It's an interesting idea to come up to use that for a simple solution.
That's one device that it's our undergraduate lab. Actually, they cut vinyl sheets, but apparently it is already computer controlled. And the graduate students working on that, Zion, she was actually the one that came up with this idea, to my surprise. And I think you will appreciate more the value of this. And I'm glad you picked up on this, because the value of it, after a significant a period of struggle trying to fight laser-induced graphene production. And Dr. Laktakia knows that. And we even approached some colleagues at Penn State who told us that we can produce laser-induced graphene designs in the size of centimeters. He is there, he can confirm that. Well, at the frequency band of the compact radar, we need 10 lambda by 10 lambda boards in order to verify this experimentally. So this 1 centimeter thing doesn't work. Then it came the idea of carbon fibers and the anisotropy. And when you put them in multi-layer, in order to make them isotropic, you don't really know what characteristic you are looking at with all these glue layers in between and so on. So the idea of using this conductive film was as simple as it sounds. It was a breakthrough for our project, actually. And Zion submitted a paper for the IEEE transactions, antennas and propagation. So those of you who are on the reviewer panel, please accept our paper. We can give you more information about this.
Thank you. Well, we have a question from the chat, and then I'll go ask if anyone has an oral question. Do you see if there is any application in AI and CEM in medical imaging design, such as better MRI scanners?
Yes, and actually, when we published a couple of papers about using AI using our device, and in both cases, in both publications, we have a long list of references of people AI to improve the quality of the images, or to better cluster the images, or to better classify the images, and so on. So there is a huge effort in the medical community to using AI regarding classification of imaging, identifying of disease, and so on. We had to reference this because we were asked to, but it has nothing to do really with what we were proposing at that time. But we needed to show what we are developing is distinct from what people are doing in the other area, namely trying to focus, because we are both using the images and so on. They are using the images in order to identify disease and so on. In our case, we're trying to use the capability of our device. For the COVID-19 paper, we basically got some images of COVID-19 images patients, and we looked at the different injuries. Sometimes there are multiple injuries in the lung. There is sometimes there's large areas of injuries. There are multiple, and so on. In that paper, we examined our ability of our design to detect or monitor these patients under this varying condition of injuries, multiple injury, large injury, how close the injury, close to the receiver, or how far it is, and so on. And also the effect of the lung conditions. If the lung is with heavy water, is more difficult to detect the COVID injury, or if it is normal lung, it's easier, and so on. So you see all this variation, the lung characteristics, energy size and location, and so on, that played a role in producing the paper that we published about a year ago or so.
Great, thanks. Any other questions?
James, I think there is one on Q&A.
Can you please read it for me, please?
Yeah. I mean, I read the one that I see in the Q&A. Do you see another one?
I see one from Bang Nahan.
Yeah, I think I asked that. The MRI scanner one, yeah.
Okay, all right.
Someone, yeah, wondering if the PDF file will be available.
And also people can unmute themselves and ask questions. Magdy, I'm going to ask you a question. This is really meant for graduate students and postdocs. I'm asking on behalf of them. So, of course, electrical engineering students don't learn AI, etc. Okay. Do you have a favorite book or resource that you can recommend to students and graduate students and postdocs, and even older people like me who would like to know new things?
Excellent, excellent. You remember these two books that published by Springer?
Yeah.
The second one, there is a chapter on genetic programming in metamaterial designs.
Right,
I think that is chapter 22
right.
by Jill Nakatsa, our graduate PhD student. And of course, our names are there. And there are excellent references there about books about genetic programming. As a matter of fact, some of the images were taken from there and so on. So these are, so there are some good references there, excellent references, actually, not only good, on different bio-inspired techniques and genetic organism, genetic programming, and all that kind of stuff. It's all included there. So you can start with the chapter there. I think it's chapter 22 in that book, and take it from there. And then, of course, you go Google, and you will be overwhelmed by how many people working in this area.
Well, that's the reason why I wanted you to recommend something. So what I am going to promise is if somebody writes to me, I will send them a PDF of that chapter.
Okay. Oh, wow.
Yeah.
Okay.
So
because it has some very good references there, yes.
I have another question for you. So you focused, when we talked about bio-inspired computation techniques, you focused on genetic programming. And you showed the difference between genetic programming and the genetic algorithms. So that was, by the way, very interesting for me. I did not know that difference. But I want to ask you, what do you think about particle swarm optimization that I find many people using nowadays? How does it compare in your mind to genetic programming?
Well, I have to admit that we haven't used the particle swarm or others. Our use of genetic programming actually came out of an essential needs. We were working on a project that we're trying to identify buried objects that came out of the Second World War, and they were using some of the Hawaiian land as practice areas. So there are some buried object, unexploded ordnance, which are metal, that are still buried in the land, and therefore the land can be used for development. And our project was how we can effectively detect of those, because the detection techniques that they use in mainland don't work in Hawaii, simply because the nature of the soil of Hawaii is volcanic nature, is iron saturated kind of land. Therefore, the ordinates there are unexploded ordinates, are metal, buried in metal, and therefore it's very difficult to detect. So we were using actually genetic programming in order for detections. We're using Brony method and genetic programming together. And there we published actually a paper, one of our first paper, you'll find it in the chapter, about a comparison between genetic programming and neural networks at that time, because you can also get that by training neural networks. And we examined three levels of neural networks. You have that reference in the chapter. 3 levels of neural networks, and compare them with genetic programming, try to identify targets from images and so on, and based on the natural frequencies. So that comparison we made, and genetic programming for the cases that we studied outperforms neural network in this case.
I see.
Doesn't mean that we can increase the layers in the neural network and improve it, but I'm saying based on what they have done. So there are comparisons that you can make these techniques. In this case, for classifications. So beside the fact it improves in accuracy and improved in classifications and so on, there might be some differences between these different techniques in a specific areas of applications. Some of them fit some application better than others. For example, when we said the reinforcement learning, we decided to go with the reinforcement learning for the renewable energy application, because there was no known model. There is nothing to model in a neural network. I'm just trying to emphasize that some of them are better fit for a specific application than others. Of course, I'm not an expert on that, but that is one additional consideration that you need to take into account. That's obviously an excellent question that requires more in-depth. Somebody who wrote a book in that area can answer it much better than me.
Thank you. Thank you. Do we have other questions from the audience?
Well, we've been over an hour, so I don't know if we want to keep everyone too long, but I think, would you be willing to entertain questions if people follow up with you, Magdy?
As you saw, Jensina, that I said, please keep in touch in my last slide.
That's true.
Yes, absolutely. I'd
right.
love to do it. I'm really very grateful to be a part of this. Thank you, you and Aklish, for inviting me for this innovative lecture series. I wish you guys success, inviting more people and getting more participation. It's great. Thank you very much.
Thank you, Magdy.
Yeah, thank you. I don't want to cut it short, but I know we're well beyond an hour. So, but thank you so much for everything.
And
Thank you
I want
much.
to add a thank you to Sheng Cheng for helping us with the arrangements here. Thank you, Sheng Cheng. Thank you.
Thank you all. That's been great.
Okay, wonderful. Well, goodbye.
Goodbye. Thank you.
Bye. Thank you.
Appreciate you. Bye-bye. Thank you. Bye-bye.